Remember, we're doing these combination circuits, and in this one I just want you to find the equivalent resistance. So with those, you start out with the smallest part, either series or parallel, and actually here you have two starting points. If you could pick, you just pick one of them. You combine those resistors, and then you start moving out from there. If you didn't get your exam last time, anybody not get their exam? Stephen, at all? All right, we'll do just a few more seconds. A few more seconds. I'm going to stop at 2:15. 2:15. All right, good job. So on these, you want to start with the smallest part that's either series or parallel. So we'll start with this, or you could start with R3 and R4 because they're both in parallel. These give me an equivalent of 1 plus 1 equals to 2. And then let's go ahead and do these two as well. These give me an equivalent of 1 over 2 plus 1 over 2, and that's equal to 1. I'm going to go ahead and redraw it because we have some other questions that are associated with this circuit. So I'm going to go ahead and redraw it in a slightly simplified format. Like this. I have 2 ohms up here. I have 1 ohm. That's the one that I just found, the equivalent. And then I have another 1 ohm. And so now I find the equivalent of this. That's 1 plus 1 equals 2. And so I have a 2 and a 2 in parallel. 2 ohms, 2 ohms. And then that equivalent is 1 over 2 plus 1 over 2. And that's equal to 1. So 1 ohm is the right answer there. Let's try the next one. For the circuit in that figure, what is the potential across R3? What is the potential across R3? Y'all have the circuit in front of you? Anybody not have it in front of you? All right, what is that potential across R3? All right, let's do about 15 more seconds, about 15 seconds. Stop at 110, 110. Okay, good. B is right. 6 volts. Let's take a look though. Way you want to do this is start sort of at your simpler circuit and then step back. So for example, I know that I have 12 volts on this battery, so I have 12 volts here and 12 volts here. Because you know, resistors in parallel, they have the same voltage. Resistors in series have the same current, but resistors in parallel have the same voltage. And so if I have 12 volts there, that means that I have 12 volts on this resistor, and so I have 12 volts here, and, or excuse me, I'm sorry. Oh, I'll write that down. I have 12 volts across both of these resistors. Resistors in series, they split up the voltages. Resistors in parallel, they share the same voltage, but resistors in series split it up. And since these are identical resistors, that will give me 6 volts and 6 volts. I know it has to be split that way because these two resistors are identical, they'll have the same voltage, and the sum of them has to equal the total voltage, which is 12 volts. So I have 6 and 6 volts. Now let's see, what am I looking for? Oh, R3. Oh, I can just stop right here because I know that I'm looking for the voltage across this resistor. And so if I have 6 volts across the equivalent of those two resistors, then I know that I have to have 6 volts across both of these. And so R3 has 6 volts across it. So the answer is B is the right answer. Hey, Neutron walked into a bar, and it says to the bartender, "How much for a drink?" And the bartender says what? "No charge." Y'all have heard that one, right? It's an old one. Yeah, but it's a good one. So it's worth replaying every once in a while. Let's try this one. For the circuit we just had, if you removed R3 and you replaced it, you know, with a wire, you just took that resistor out and left a wire there, what would happen to the current through R1? If you removed R3, what would happen to the current through R1? We'll see some more questions like this in the clicker in the concept test, but you'll probably see them on the exam as well. These sort of what-if questions. I'll be working that. I want to look at something back here in the back. All right, let's stop in about 10 seconds. I'll stop at 110, 110. All right, so I'm going to remove R3. See, I think B is right, but we'll check. I want to remove R3, and then I want to know what happens to the current through R1. So if I remove R3 right here, that causes well, I don't even really need to worry about what it does, because if I remove R3, since this whole thing is in parallel with this whole thing, R3 is here, R1 is here, parallel branches act independently. So anything that I do to this branch here will not affect this branch whatsoever, not at all. Because parallel branches, it's like they're all independently hooked up to the battery. So whatever I do in that lower parallel branch will not affect the upper parallel branch. So then, y'all didn't put the right answer then. No, the answer is C, that current will remain the same. All right? Doesn't matter what you do to R3, it's not going to affect R1. Now let's go back and look at that. What do you think would happen to the current through R5 if I removed R3? If I just took this resistor out, would the current through R5, I'll call it I5, would it A, increase, B, decrease, or would it C, remain the same? What would happen to current 5, the current through resistor 5? Would it increase, decrease, or remain the same? All right, most of you have the wrong answer right now, or a majority of you have the wrong answer. Think about what happens when you take resistors out of a parallel circuit. Or rather, we talked about this. What happens when you add resistors to a parallel circuit? Does the equivalent resistance go up or down? When you add resistors to a parallel circuit, does the equivalent go up or down? It goes down, right? Because when you add resistors in parallel, you give those electrons more paths to travel. So when I take out, what do I say? I'm removing R3. This circuit, the resistance, is actually going up. You're increasing the resistance by removing a resistor. And that seems counterintuitive, but it's true for resistors in parallel. That when I remove a resistor in parallel, I reduce the number of paths that the electricity can take, and that increases the resistance. So now, if I remove this resistor, how does that affect the current through this resistor? All right, we're still split. Ask your neighbor what they put, please. Share your answer with your neighbor. All right, we're a little bit better. I'm going to stop at 2 minutes. 2 minutes. Okay, good. B is right. The resistance of this branch will increase when you remove this resistor. And because the resistance goes up, the voltage stays the same, the current goes down. So the resistance here will go down. The resistance through R5. All right, let's see. One more question about this circuit. Which resistor has the least current traveling through it of these that I've listed? Is it R1, R3, R5, or do all of those, R1, 3, and 5, have the same current? All right, let's stop at 55. 55. Actually, I'll stop at 52. 52. All right, I think B is right. R3, let's go take a look. Yeah, that looks right. All right, so our current comes along here. This is 2 ohms, and down here we also said that this was 2 ohms. Right? We drew it like this. So I have the current split right here into equal pieces because each branch has the same resistance. I get 2 ohms up here and 2 ohms up here. So that means actually I'm going to get a current of 6 amps and 6 amps, which gives me a total current, right, coming through here of 12 amps. Which, since I have an equivalent of 1 ohm, that makes sense. I should have 12 amps of current. So I get 6 and 6. Over here, it splits up again into what and what? 3 and 3. These are equal resistors, so they split the current equally. So I get 3 and 3. They come back together, and I get 6 amps here. So I was looking at R1, 3, and 5. I get 6 amps, 3 amps, and 6 amps. And I was looking for the one that had the least or the greatest? The least. So it is R3 is the right answer. All right. We're going to skip the Christmas vacation. We can come back to it when we do household circuits, but it's more relevant there. And before we do Kirchhoff's rules, let's do another combination circuit, an example like you'll have on your test at the back of your book. I don't think you have page numbers, but it's 253. It's the one that looks like this, number 17. I think this is probably exam, well, I don't know. Exam 3, number 17. So I want you to find the voltage and the current for each of these resistors. To do so, you'll need to find the equivalent resistance. So start by just finding the equivalent resistance, simplify the smallest portions, and I really like to draw the circuits as I simplify them. It helps you to sort of keep track of what's going on. Give about 3 to 5 minutes. So another minute or so, and I'm going to jump in there. So we have your attention. Let me show you something with this. I like to give circuits that have nice, easy patterns that you can recognize. And you might not recognize them right now, but you will eventually. I start with this, 2 and 4, 6, right? 2 plus 4 is 6. 3 and 6, oh, well, that's something we recognize 2, right? 3 and a 6 in parallel is 2, because 1 over a third plus a 6 is equal to 2. So I get 2 and 3. 2 and 1 is 3. So look, now I have 3 and 6 again, so that's also 2. So this whole thing reduces to 2 ohms. And notice that it's in series with another 2 ohm resistor. So if I have a 2 and a 2, I'm going to write this down in a second, I just want to step you through it. If I have a 2 and a 2, that means if I have 12 volts, I have to have 6 volts here, and I have to have 6 volts across this whole big thing. Right? If I have 6 volts across this whole big thing, I have 2 and 4. This one is going to have the smaller voltage, and this one will have the bigger voltage. This one will be bigger by a factor of 2 because the resistance is bigger than by a factor of 2. And so I said I have 6 volts across all this. I'm going to have 2 volts, and I'll have 4 volts. Right? Because this is, they have to add up to equal to 6. This one is 1/2 the voltage of this one. So I have 2 and 4 volts. And then in a very similar way, I have 2 and 1 ohm here. This one will have twice the voltage. So I'm going to have 4 volts here, and 2 volts here. Right? So when you get to sort of looking at it, you can begin to spot these patterns. And you might even be able to just write down all the answers without even putting your pen to paper. But I recommend that you do write it out just to make sure that, you keep track of your thoughts. And let's do that here. So first I want to find my equivalent. I can start with this. I know that's 6 ohms. And then also here, I know that's 2 ohms. I'm going to redraw that circuit. This is 6 ohms. And actually, I'm going to go ahead and redraw this as 3 ohms because I know that's 2 and this is 1. 2 plus 1 is 3. That's 12 volts. And I redraw it again. I get 2 ohms and 2 ohms. 12 volts. And then I can just stop there. I mean, I could go on and find out that the equivalent is 4 volts. Well, yeah, let's go ahead and do that because sometimes you might not have nice, easy patterns, and you need to go through sort of the steps. So here, if I have 4 ohms and 12 volts, that means that I have a current equal to 12 over 4, 3 amps. If I have 3 amps, that means I have 3 amps here and 3 amps here. And so that means that I have 6 volts and 6 volts. But we already knew that. But that's sort of the longer process to get to that. And if it's not nice, easy numbers, then that's the process you go through. Find the equivalent resistance, find the current through the equivalent resistance, and then recognize, well, series and resistors, they all have the same current. So if I know the current in my resistors, I can find the voltage. Now we keep stepping back. I know that if I have 6 volts here, I have 6 volts here and 6 volts here because resistors in parallel have the same voltage. If I have 6 volts, that means I have 1 amp there and 2 amps here. Notice that my currents here add up to equal the total current. I have 3 amps going into this branch. So that 1 plus 2 is equal to 3. Now I'm almost there. If I have 1 amp through this resistor, I also have 1 amp here and 1 amp there. And then if I have 6 volts going through this resistor right here, I have 2 amps. That means I have 2 amps here and 2 amps here. If I have 2 amps across this 1 ohm resistor, that means that I have 2 volts. And if I have 2 volts across that resistor, I know that I have 4 volts here and 4 volts here. I know this because, well, I know the current going through here, all right, because I have 2 amps coming down in this branch, because the equivalent of this was 3 ohms, and I know that it has 6 volts. I is V over R, that's 6 over 3, is 2 amps. Now, I don't know exactly how it splits up just yet right here, but I know that over here I get the full 2 amps. So if I get 2 amps there, V is equal to IR. 2 amps times 1 ohm is 2 volts. And if I have 2 volts here, since I have a total of 6 volts, I have to have 4 volts across both of these because resistors in parallel have the same voltage. So if I get 4 volts here and here, then I can calculate the current. I is V over R, 4 over 3, 4 over 6. So my current's here. My current's blue. My current is 4 over 3 amps and 4 over 6 amps, or 4 over 3 and 2 over 3. And notice that these add up. These two fractions add up to equal 2 amps, as it should be, because the current coming in has to equal the current as it splits up. All right, so now we can go through and write our answers. I have 3 amps and 6 volts on the first one. On the second resistor, I have 1 amp and 2 volts. That's this one right here. I got the voltage, I just said 1 times 2, I times R. R3 is 4 volts and 1 amp. Again, I times R. R4 is 4 volts and 4/3 amps. R5 is 4 volts and 4/6 or 2/3 amps. And then the last one is 2 volts and 2 amps. And then if I want to know the equivalent was 4 ohms. All right, I might also ask you what is the power across any one of these resistors. So the power is 6V times I, which is 18 watts, 2 times 1, 2 watts, 4 watts, and on, 16/3, 8/3, and 4 watts. Just to calculate the power that's dissipated, how much energy per unit time is dissipated across each of those resistors. Very likely to have a combination circuit, sort of this difficulty, similar but different, number of resistors, sort of how they're laid out, but very similar. If you can work this one and know how to do it, you should be okay. There's more practice on the old exams. There's also 1 or 2 in the homework. So make sure you know how to do these combination circuits. All right? Spend a little time with them. Sometimes they're a little hard right at first, but once you get a hang of it, they become a lot easier. And you begin to see these patterns, and you begin to see how the voltages are distributed. It's sort of like the matrix, right? You don't see just ones and zeros anymore. You see whatever they see in the matrix. Okay? Let's do a few more clicker questions. I have, and go to your appendix. These will help you to see that pattern. And by the way, don't forget the Chem Club is hosting that fundraiser this week. It's for Pi Day, but it's helped them raise money for these various special events that we have in the department. I brought in the containers there in the back, so if you wish to donate, you don't have to, but if you wish to, they're right over there. This is for the pie and the face thing. Dr. Pockerell is in the lead. He put his own money in the jar. And I don't think that's really allowed, so, but he's a shady character. You gotta watch Dr. P. Well, let's try this question first. What is the potential difference across each resistor? All right, I'm going to stop at 120. 120. I'm sorry, you didn't have time?
No.
I'm sorry, it's because I was going on about that fundraiser, right? I'm sorry, Brennan. All right. If I have 3 identical resistors, they split it up evenly, right? They all have the same voltage, and so it doesn't matter what the resistors are. They could be 1 ohm, or they could be 1,000,000 ohms, a mega ohm. They're still going to have 3 volts across each one. Now, if it's 1 ohm or a mega ohm, it will affect the current. The bigger resistor will have a much smaller current But here I have the voltages will all be the same. 3 volts is the right answer. Hey, why did the pig leave the costume party? Because everyone thought she was a boar. All right. In the circuit below, what is the voltage across R1? You can go through and calculate it, but try just looking at it and thinking about how the voltages are distributed. All right, we'll stop at 50, 50. Okay, so the hard way to do this is say your equivalent is 6 ohms. 6 ohms with 12 volts, that's 2 amps. And 2 amps times 4 ohms is 8 volts. 2 amps times 2 ohms is 4 volts. And so I'm looking for the voltage across the R1, so that will be 8 volts. The easier way to think about this is this resistance is twice this resistance, and so it's going to have twice the voltage of this, but the 2 voltages have to add up equal to 12, 8, and 4. That fits that bill. I'll try to use nice easy numbers on the test like that so that you can do those sorts of things just in your head. But the answer there is 8 volts. But if you don't want to do that, just find the equivalent, find the current through the equivalent resistor, and then you can calculate the voltage across each. For this circuit, what is the current through R1? Think about our resistors in parallel. And what is the current through R1? I'm going to ask you another question after this, which is, what is the total current in the circuit? So begin thinking about that if you've already answered this. What is the total current? But right now I want to know what is the current through R1. I'm going to stop at 1 minute, so about 8 more seconds. 1 minute. All right, that's right. Now I also want to know, the answer for that one was D, and I'll come back to that. But right now I want to know, what is the total current? So there's some amount of current that's coming off of this battery and going into that circuit. What is the total current? A couple ways you could get this answer, but there is one way that's easier. What is the total current? Y'all doing really well. All right, let's stop at 45, 45. All right, E is right. So very good. Let's go back to the first one. What is the current through R1? R1 has 10 volts across it. Both of these have 10 volts across them, actually. And so I is equal to V over R, 10 over 5, which is equal to 2 amps. All right, so that would be the answer for the current through R1. But if you want to know the total current, the easiest way is to say, well, gosh, I got 5 amps up here. 10 over 2 is 5. 10 volts divided by 2 ohms is 5 amps. If I have 5 amps here and 2 amps here, the total incoming current has to equal the current in the junctions. So I have 7 amps total. Another way that you could approach that is you could say, what is the equivalent resistance? 1 over 2 plus 1 over 5. What's that? 1 over 5 over 10 plus 2 over 10 is equal to 10 over 7. 7/10, yeah, 10 over 7. And then that's our resistance. I is equal to V over R, which is 10 over 7, which is equal to 7 amps. So you could do either way, but I think the first way is a little easier. You don't have to find that equivalent resistance. Oh, yeah, D is right for that one. All right, what happens here? I have these resistors in parallel. What happens to the total current in the circuit as I add more resistors in parallel? So I have these resistors, then I just keep adding more and more resistors in parallel. What happens to the total current in the circuit as I add those resistors? All right, let's stop at 45. 45. Okay, very good. So I understand why you would put decreases, because you think, well, if I increase my resistance, then I'm going to decrease my current. And you would be correct in saying that if you increase the resistance, you decrease the current, because you're adding more resistance to the flow of electricity. But as you add resistors in parallel, what happens to the total resistance? Well, adding resistors in parallel decreases the equivalent resistance. So here, you're decreasing the equivalent resistance, and that causes the current to increase. Or you can think of this as, you know, if I have a certain voltage here, I have that same voltage on all of these. And so as I add them, I'm also adding a current. And so I add that current, then this incoming current will increase. Every time I add a resistor, then it's going to increase that current by whatever amount that resistor draws current. It's like in your house, right? Your house is laid out on a parallel circuit. As you add resistors, your clock or your radio or your bathroom heater or whatever, as you add those resistors on your circuit, it draws more and more and more current until eventually, you know, your circuit breaker kicks off, which is what happens. We'll talk about that a little later. All right, what happens here? If a wire is connected across this bulb, what will happen to this circuit? All right, we'll stop at 45. 45. Oh, no, that's not right. C is right. Electricity takes the path of least resistance. That's where that sort of adage comes from, that you take the path of least resistance. It comes from electricity, that it will take the path of least resistance. And so a wire has basically zero resistance, very little resistance. So as I have my current come along here, if I add this wire, which is basically a path of basically zero resistance, practically all of it will go through. Right? Practically all will go through. And so we would say then that the light bulb would just go out completely. So C is the answer there. Practically. The wire does have some resistance, but it's so different. It's so much smaller. Yeah. Yeah.
And like in question, 4.2a, why doesn't all the current go through the 2 ohm resistor instead of the 5 ohm resistor?
Oh, because the wire basically has zero resistance.
Okay.
All right. And whereas here, these are just different resistors. So we have some resistance up here, but it's not zero resistance.
Okay. So it only matters if it's 0 versus.
Yeah. So, oh, I understand.
Because it has less resistance.
Right.
That's
Yeah.
the least resistance.
I understand. Yeah. All right. Yeah. So that is confusing. So the current will actually split up according to the proportions of the resistance. So those with smaller resistances will get bigger currents, and those with bigger resistances will get smaller currents. All right. Sorry for that. I know that's confusing. Is this clear now? Okay, what will happen here, that's really just sort of leading into this. If I put a wire across light bulb B, and then I close this switch. So effectively, I'm removing B and putting in a wire. What's going to happen to bulb A? Brighter, the same, dimmer, go out, or does it just explode? All right, let's stop at 50, 50. Okay, so the answer is A. Notice what happens. Let's say that I have a 12-volt battery. That means that I would have 6 volts and 6 volts when both light bulbs are on. However, if I take one of them out, if I make this 0 volts, then I'm going to have 12 volts across the first one. So if I have a bigger voltage, voltage is energy per charge, I'm going to be pushing more energy through that light bulb, and that's going to make it brighter. How much more brighter is it going to be? Or how much brighter will it be? Well, will it be, let's do it as a clicker question. Will it be twice as bright? 4 times as bright? Or 8 times as bright? That's your main voltage. Will it be twice as bright, 4 times as bright, or 8 times as bright? The only thing that you're changing the voltage here. And so we want to think about how does changing the voltage affect the power? Because you're also changing the current. But, how much brighter is it going to be? And when I say brightness, I mean power. Power is related to brightness directly. All right, you're all wrong, except for one of you. Everybody's wrong. Remember our power expression. I'm going to show you. Power is equal to V times I. And so you say, well, I've doubled my voltage, so therefore I should double my power, right? But you're also doubling your current, because if my voltage goes up, my current also goes up. Another way of looking at this, we have these alternate expressions for power, V squared over R. This is really a better way to think about this, because R is constant for the light bulb. If I double the voltage, I'm going to do what to the power? All right? So, there you go. You're all switched around. So, I'm going to stop at 117. Okay, very good. B is right. It'll be 4 times as bright. So doubling your voltage will cause an increase of a factor of 4 for your power. Let's see. Help me out with this one. This one's kind of tough. A drunk, he staggers out of a bar, and he opens the door for this couple that's coming in, and he just lets out this loud burp right in front of the couple. Nice couple. It's kind of rude. And so the husband, he says, "How dare you belch before this lady?" And the guy says, "Oh, I didn't know she wanted to go." Not very good. You get it, they're like, have belch before this lady. All right, I'll have to work on that one a little bit. All right, but I told you the answer, so you get a joke in progress. All right, what's that? All better. Let's see, what time is it? Yeah, I want to do something before we cut out. We'll finish those up next time. Y'all will do assessments at the end of the semester, and that does all its business, and that's useful because it helps me to plan for next year. But I like to do midterm assessments where you just tell me one thing that you like about the class, and then one thing that you would change about the class. And then if I can make changes mid-semester, then I certainly will if it's something that I'm able to do. So please take out a sheet of paper. Don't write your name on it. If you want to, that's fine, but you don't have to. I'm not going to, they'll be anonymous. You can just set them on a back table as you walk out the door. But one thing that you like, and then one thing that you would change about the class. Or one thing that you like, and one thing that you would change about the class. It's on a sheet of paper, and you can put it back on the back. And remember, if you wish to, you don't have to, but if you wish to, the NCSS fundraiser's back there. That's for the pie and the face. I think it's on Friday. If you're not able to come, that's fine, but we'll take pictures, and whoever it is, I'll show you on Monday morning.
Are we collecting money until Friday?
I'll find out. Yeah, I think it doesn't say. I think we're collecting money till Friday. It'll probably be about lunchtime. Yeah, yeah, collecting till Friday. Yeah, collecting till Friday.